Once upon a time, on a planet called Earth, a mathematician sat down to solve a problem. What is the square root of -1? This one problem sparked a huge wave of controversy in the mathematical community and spawned a new form of mathematics. Welcome to episode 16 of Dyllon Explains Everything. My name's Dylan. In case you couldn't tell by the title, I'm the one explaining everything, including the topic of today, imaginary numbers. I'm going to be running through a lot of facts, so if you're curious as to where I get my information, be sure to check the description below for a list of links. Imaginary numbers might seem boring at first, but I assure you, they're very interesting and useful in several ways. But first off, I'm sure that in elementary school and middle school, they told you that you couldn't take the square root of a negative number. Well, they also told you in kindergarten that you couldn't subtract a small number by a bigger number, and they also told you that Paul Revere rode on a horse into a city saying the British are coming, but none of this is actually true. When you ask for a square root of a number, you're really saying what squared equals that number. For example, the square root of 25 is 5, because 5 squared, or 5 times 5, is 25. Both negatives, this brings a problem. A negative times a negative will always be a positive, and a positive times a positive will always be a positive. The only way you can get a negative is by multiplying a negative and a positive. So how can you square something and get a negative? This is where imaginary numbers come in. Now, imaginary numbers might sound like something that's, well, imaginary, but I assure you they're no more imaginary than negative numbers. They're only called that in order to make fun of them and place them outside the realm of real numbers like these. So how does this work? Well, first of all, we have to define the square root of -1 as I. This stands for imaginary and can then be used to make the square root of any negative number. For example, the square root of -4 is really just the square root of -1 times the square root of 4, which gives us I times 2, or 2I. Now that we understand how imaginary numbers work, this is where things get tricky. You can place any number on a number line, right? I mean, you can have everything 0 through 5, or even negative numbers. You can put pi right past 3, or 1/2 between 0 and 1. But where would imaginary numbers go? Well, imaginary numbers are shown as going here. Basically, the entire number line becomes what we call a number plane, with real numbers going left and right and imaginary numbers going up and down, like I or 2I or -2I. But what does that make this space in between? This is where we put numbers called complex numbers, like 2I plus 1. This is an imaginary number plus a real number, and therefore it needs to be represented on the number plane between the two. This means that there's actually more complex numbers than both real and imaginary numbers combined. So why is any of this important? Well, before I get to that, I'd like to point out that a lot of things in math, at least in my opinion, shouldn't have to be important to be talked about. I mean, a lot of the people who found out about these numbers were pure mathematicians, not applied mathematicians. Actually, the first time that these numbers were talked about was in the 1500s, when people started working on third and fourth degree polynomials. They needed an advanced form of math that could solve the square root of negative numbers, so they started looking into things like I. They started being talked about again in 1545 when a mathematician named Girolamo Cardano made a book called Ars Magna, where he found that this problem translates to 5 plus or minus the square root of -15. He found a mathematical solution that required imaginary numbers, but he brushed them off as useless, even calling them mental torture. Throughout history, multiple mathematicians encountered problems that needed the square root of a negative number, but they brushed it off as impossible because they didn't like imaginary numbers. These included people like Isaac Newton, who were solving real-world problems. Then, in 1637, a mathematician named René Descartes made the standard for complex numbers, a plus bi. Also later on, a mathematician named Raphael Bombelli started working on imaginary numbers. He was a huge believer in them and started pushing them onto the public, trying to spread awareness about them. He even proved that -I times -I was 1, and made multiple proofs about conjugation, or using imaginary numbers to make real numbers. Then in 1685, a mathematician named John Wallis actually showed how you can use this graph to graph complex and imaginary numbers on the number line. And later, a mathematician named Caspar Wessel actually proved this in a paper, but no one was listening to them. Then, in 1777, our old pal Euler used I to represent the square root of -1. And then a few years later, in 1804, a mathematician named Ab Bowie agreed with John Wallis's work and started spreading the word about it, but didn't get very far. Then in 1806, just a couple years later, a mathematician named Jean Robert Argand started spreading the word of how to graph things on the complex plane, which is now called the Argand diagram. Finally, in 1831, a popular mathematician named Carl Friedrich Gauss started spreading the word about the Argand diagram and popularizing the Descartes notion of complex numbers, finally allowing the mathematical community to accept complex and imaginary numbers. Several other mathematicians throughout history have worked on notations of imaginary numbers or how to calculate or graph them, but why do they care so much about them? I mean, a lot of these guys were pure mathematicians, but what about the applied mathematicians? Why did they care about imaginary numbers? Well, it's useful for things like sound and waveforms. I won't get into it too much because there's a lot of complicated math, but using something called the Fourier transform, we can take any frequency and turn it into individual sinusoids or sine waves, which look something like this. This is great and all, but we don't use this in real life, do we? Well, when you look at someone who's mixing sound on something like a soundboard and you see the cool little waves where it shows which frequencies are going up or down, that's using the Fourier transform and by extension imaginary numbers every time you listen to music. But let's talk about something else we use on a daily basis. AC or alternating current, electricity. Electricity is going in sine waves that can be measured as AC. But when those sine waves have to be added together, you cannot do it easily without imaginary numbers. The result you get is using imaginary numbers, but it's a very real current that could still kill you. Another thing that these are useful for is the Mandelbrot set. Now, this is technically not applied mathematics, but it's still fun to talk about. Now, if you've ever looked into fractals, you've probably seen this in action. It's basically an equation using imaginary numbers that allows you to make a fractal that repeats forever. So you can zoom in on the edges and it'll never go flat. They also help with the quadratic equation, quantum physics, quantum computing, relativity, fluid dynamics, and much, much more. But I isn't the only imaginary number. In fact, j and k are both imaginary numbers. They're both the square root of -1. And in order to put these into an equation, we have to put them in this form. But if we always have to put them in this form, how would we multiply two imaginary numbers like I times j? This was discovered by a guy named William Rowan Hamilton on the Broom Bridge in Dublin. He was thinking about this problem while he was walking on the bridge and figured it out, so he wrote it on the side of the bridge where it is today. Remember, I squared, j squared, and k squared are all -1, but what William showed was that I times j times k was also -1. Allow me to explain why. The reason this works well is because if we then multiply both sides by k, we can cancel out the k times k as -1, and then divide both sides by -1 to get ij equals k, solving the problem from before. This allows us to put any of them into this form, meaning that we can prove that j times k is I and that k times I is j. But for weird reasons, there's no commutative property with imaginary numbers. So even though I times j is k, j times I is -k. Imagine a circle of arrows and these letters in it. I goes to j, j goes to k, k goes to I. Now, if we multiply any two going clockwise, we get a positive number. So I times j is k, j times k is I, and k times I is j. But if we go counterclockwise, we're introducing a negative. So j times I is -k, I times k is -j, and k times j is -I. Now I could try to explain this, but I'm going to be honest, I don't even fully understand why that is, and this isn't even the most complicated stuff. I mean, we went from having one type of number, real numbers, to 2 types using I, to 3 types using J and K, and we could take it a step further with 8 different types of numbers. But this is very complicated. Now, whether you think that imaginary numbers are too complicated, or you just think they're boring, or maybe you're like me and you think these are really interesting and fun to talk about, you have to admit they help us on a daily basis throughout our life, and we wouldn't have science today without them. With all that being said, I hope you enjoyed today's video more than people enjoyed imaginary numbers between the 16th and 19th centuries. And if you did, be sure to let me know and look out for my next video, which comes out every Saturday at 10 a.m. And if you have any thoughts, questions, or suggestions, be sure to leave them in the comments below. And remember, my name's Dylan, and I explain everything.